Hello, this is Dr. Delacorte back with Physics 313R. Today we have Lecture 8, Quantum Gates and Circuits in our Introduction to Quantum Computing. Let's jump right in. As you recall, we are using the book Quantum Computing for Everyone for the basis of all of this, so I highly recommend you to read in that book. I'm going to skip the recap because we've done it now quite a few times. We just remember that measuring is what forces a qubit into a final state. Before the measurement, it sits in any superposition of possible outcomes. Great. We have all of this linear algebra at our disposal now, so we don't really test often if a set of cats is an orthonormal basis, but we very often have to express cats in that orthonormal basis, and to get the probability amplitudes, we need this rule quite a bit. And then finding the length of the vector is something we sometimes use as well. Great. So qubits can be represented as spins of electrons or as polarization of photons. And when you have two qubits, they can be entangled. So if Alice and Bob have both a qubit and they underwent some manipulation so that they're entangled now, when one of them makes a measurement, it will define the state of the other one. And so that's quite interesting. We learned that this entanglement makes the two qubits share a global property with each other, and there's no hidden variable, but there's just this global property that combines the two individual qubits into a combined system. Great. Last time we looked into different gates and logical operations, and we saw that there are specific gates that we call reversible. The special thing about reversible gates is that they have the same number of input and output bits, and so it's possible to deduce the input from the output. That's what makes them reversible. The trick to that is to add either additional input bits, ancilla bits, or dummy bits, and then also produce some output or garbage bits that you don't need. And in order to build these, we had to use an operation called fan out, which works in classical computers quite well. If you have an electrical signal, you can just branch it off and send it in parallel wires. But if you have qubits, you will see that that would be a bit more difficult. And we saw that some of these gates are functionally complete, which means you can build any more complicated circuit just using those specific gates, like the Toffoli or the Fredkin gates. Great. Now let's talk about quantum gates. What does a quantum gate do? A quantum gate is effectively like a measurement. It just rotates our qubits. So if we have, for example, Alice that sends a qubit through like an electron with a spin through a magnetic field, that electron will either be deflected up or down. There's a certain probability associated with each of them. If that electron was flipped on top, we could imagine that that electron traveled some path and eventually ends up again at the very same measurement device. And you could measure it twice, and you would assume that the same result occurs. However, what might happen is that somewhere along the path, that electron interacts with something, which we'll call a gate. And what that gate does is it takes the qubit and spins it a bit, and it rotates it. And if it comes back after this rotation, you will potentially get a different outcome. And so we say anything along the path that rotates the qubit is a quantum gate, and rotations done by quantum gates are the same as multiplications of a vector with an orthogonal matrix. All right, so what does this really mean? If we have a fixed measurement, we only need one ordered basis. So if this is our qubit, then we might want to measure it in a certain polarization of the magnetic field with these north and south vectors here. And those are oftentimes then represented just as 0 or 1 for the 0th and 1st basis vector. So any state that our qubit has will be a linear combination of these basic vectors. We just don't know what A0 and A1 are. But what we do know is that the product of their squares has to be 1, because we are dealing here with probabilities once they're squared, and the sum of all probabilities has to be 100%. Okay, so if you happen to have two qubits, then we represent them as the tensor product of the individual vector states. So we have 1, 0 and 1, 0 that are vector producted, tensor producted, and so the other combination of bases as well. This can be shortened by writing these states as the 0 and 1 vectors, or we saw last time we can get rid of the tensor product by using the convention that when two cats are written next to each other, we assume there's a tensor product between them. Now, one more convention is let's get rid of these extra brackets and just write them together like that. So whenever you see now a bar with two numbers, 2 bits, and then a closed bracket, then you know that these 2 bits represent actually 2 basis vectors, and the tensor product between them is meant. So this 0, 0 here corresponds to a 4-dimensional state. Right. And if you have these 4 different vectors, they actually open up a new vector space, that's the R4, and in that 4-dimensional vector space, we can now represent again any arbitrary vector as a linear combination of these 4. And so we can build a linear combination with the coefficients R, S, T, and U. And we saw before that we can see if 2 vectors or 2 qubits are entangled by comparing RU, the product of R and U and S of T. Okay, great. So let's look at the C NOT gate. So that is the controlled NOT gate, controlled because we have not only the Y that we want to flip around, but we also have this control bit added, the X at the beginning and the X at the end, which makes it so that the outputs are allowing us to calculate what happened before. And so the C NOT gate is a controlled NOT gate, but what it actually calculates here, you see it's neither of these is the NOT of the other one. This is actually this exclusive OR that is being implemented here, or the addition modulo 2 operation. Okay, and we can rewrite this truth matrix more simply as the inputs were 0, 0, 0, 1, 1, 0, 1, 1, and the outputs as such. Okay, because the vectors always need to be considered as a pair in their tensor product state, which is not a single vector, it's a single qubit state, but it's the 4-dimensional combination of 2 of those guys. Okay, so the basis set that we're dealing with, the ordered orthonormal basis set is this guy here. And any vector can be represented as a linear combination. Any of these vectors can be sent through the C NOT. If you run it through the C NOT, what will happen to it? Well, the 0, 0 we can look up is mapped to 0, 0. Okay, the 0, 1 is mapped to 0, 1. The 1, 0 is mapped to 1, 1. So the T that used to be 1, 0 is now the T 1, 1. And the 1, 1 is being mapped to 1, 0. So we see that U and T have switched positions. So whatever these matrices, what they do is they rotate basis vectors around. The way we can represent the C NOT gate looks like this. We have here coming in a qubit in superposition and a qubit just in state of 0. And after they are being subjected to the C NOT gate, then they are living in this superposition state. Okay, and that we have seen before is an entangled state, right? This is the same thing that we had before, 1 over square root of 2 and then 2 times the same vectors plus 1 over square root of 2, 2 times the other vectors. Very nice. So mathematically speaking, we are taking this first vector and we're calculating the exclusive OR with the other vector. And then if you do the math, you end up with this entangled state. So you can see that this multiplication, tensor product like multiplication of the 0 vector just gives you exactly this result. Wonderful. So a C0 gate can be used to entangle two qubits. If you have one that's in the superposition of the two basis states and one that's just in zero state, the C0 gate will get you the nicely entangled ones. So what are quantum gates? We saw that the C0 permutes, also rotates basis vectors around in the set. And whenever you just have an ordered orthonormal basis set and you take two of these vectors and you swap them around or permute them, then you're still going to have the same number of basis vectors. So they're still going to be all length one and they're also be orthogonal to each other. But since it's an ordered set, by permuting them, you're going to have a different ordered set. Okay. So all that does is it gives you a different basis to measure in. And we will see that this calculation, this permutation, always happens when you apply an orthogonal matrix to your vectors. And so what we take away from this is that quantum gates always describe operations by orthogonal matrices. So mathematically speaking, when we do apply a quantum gate, we just multiply things by an orthogonal matrix. In the experiment, obviously, it's a lot more complicated, but we're not going too deep into the experiment here. We're just trying to get a mutual language that we can use so that next lecture we can start to actually dive into the algorithms. And so for these algorithms, it will be very important that we get good at these matrix multiplications. So let's just remember that when we have a classical computer that consists just of bits in 0 and 1, we have one of two options. We can either keep a bit in its current state, or we can flip it. It's really the only thing you can do. If you have a quantum computer, however, and you have two qubits, there are infinitely many ways of putting them into superposition of each other. So you have just a lot more degrees of freedom to do things with them. Okay? And from now on, quantum gates always mean for us orthogonal matrices. So let's talk about different gates. Single qubit gates. So how many ways can you change a qubit? Can you change a bit? We just saw a bit you can either keep or switch. That's it. A qubit on the other side, you can switch in any way you want because you just change the coefficients in the superposition and then you can find any combination that you'd like. And you can describe that a bit more in your journal because I think it's a point that's not well understood the first time it's heard. Okay, great. So let's think about what we can do to a qubit. Since there are many things you can do to it, infinitely many things, how many of these should we worry about? And it turns out that there's actually only a few things that we need to know in order to understand the basic algorithms. So we focus on basic rotations of orthogonal matrices. The first one of those is the very basic identity matrix, which doesn't do anything. So if you have a qubit in a superposition and you apply this gate to it, you are multiplying by 1 effectively. So nothing has happened. And then we can think about this mathematically, visually maybe. What is this gate 1, 0, 0, 1? So if you think about the coordinate system, the 1, 0, let's make it north pointing. This is this guy here. And then the other one might be 0, 1 pointing to the right like that. So this might be the basis that you measure in for the I. For the Z gate, it looks a bit different. You are still going up on the first one, but then the second one is actually pointing to the left. It's a negative sign. And when you apply this one, you are going to change the phase of A1 here. So the probability amplitude has changed its sign. And that will be useful at times. So these are, by the way, examples of Pauli matrices. So there are 4 of them. This is I and Z. Then there's the X one. That's the one that flips the gate. So what does this one look like? So the first one is not 1, 0, but it's 0, 1. So you first go here, and then you go up. Now, this here was the first and this one was the second. Now it's the other way around. This one is the first and this one is the second. And because it's an ordered set, it gives you different responses. So it will change the coefficients between the two. And then lastly, we have the one where it switches the coefficients and gets your minus sign, the Y gate. Okay, great. Another one that's important is the Hadamard gate. This looks like this. Where's that one coming from? If you think about it, you have here a vector 1, 1. So that might be this guy. And then a vector goes 1, minus 1. So if a 1 goes up and a minus 1, it might be right here. So this one here, in order for these vectors to have a length of 1, since they have x and y components of 1, we need to make sure that the length of this guy here is 1 to the square plus 1 to the square is square root of 2. Since this would be square root of 2, we have to divide the length of this vector by 1 over square root of 2 in order to get to make sure that these basis vectors in the gate have length 1. Okay, this is why the square root of 2 is there. Otherwise, it is just this rotated, this rotated basis set. Okay, cool. So that one will be very important for us. Why is that one so cool? Because it allows us to take the basic vectors 0 and 1 and to put them into this superposition that we have already found useful before. So if you run a basis vector that is in the 1, 0 state and run it through here, then you're going to find it in a superposition with equal probability to be in 0 or 1 state afterwards. So that's quite nice. Great. How do you represent the Hadamard gate? You just make a box and write an H in. So that means when the 0 comes in, then out comes the 1 over square root term with the both basis vectors there. Okay, great. Cool. Now the big question is, are there any universal quantum gates? We saw that the Fredkin and the Toffoli gate, for example, were universal gates because you could build anything out of them. Turns out that with quantum gates, because there's an infinite number of superpositions you can form, there's no, mathematically speaking, complete set of discrete gates that can build an infinite number of other things. But you can approximate it pretty closely, and the things that we have introduced so far, they'll get us far enough. Okay, and you can, if you want to, philosophize about this in your journal and write down why you think there cannot be universal quantum gates. All right, now a very interesting result, the so-called no cloning theorem. Let's look at this here. The question is, are we able to build a gate in which we put a specific qubit x and then some extra input, whatever, a 0, and make it so that the gate clones the information in x into 0. Why would you ever want to have that? You might recall that some of our classical gates had these fan outs where you would have an x here, and then after the fan out, you have an x here and an x here that you can then use for something in the future. And so the question is effectively, are we able to build something like that for qubits? Can we take a qubit and send it in 2 different ways? Well, let's assume that we can and see where it takes us. Let's assume we can build a gate G that can do that. What does that mean? That means that this gate should be able to take the state 0 as x input and then the 0 that comes in here and then clones it. So x turns into 0 and this one turns into 0. Should be possible, right? If G exists. And then the shorthand for writing this is with this new simplified notation. Okay, if that one exists, then there should be also possible for us to put in a vector 1 here. and then have G copy it, and then we have a 1 here and a 1 here. All right. So this should be a 1 here. Okay. So if that's the case, then we can think about thirdly, what we should be able to do is we should be able to say we take a vector in a superposition of both states and throw it through here. And if we put this qubit in superposition in up here, we should be able to get something. Wait, what am I doing here? 1 second. Oh yeah. All we're doing here is we're trying to see what happens if we put a qubit in superposition in. If you put a qubit in superposition in, then it will simplify to 1 over square root of 2, and then you have the 0, 0 state and the 0, 1 state. Hold on a second. Okay, so I skipped a step here. This is why I couldn't see directly where we got this guy from. So if G exists and clones this qubit here, then after G, let's put a little star here. After G, we would have this qubit twice, and we have to multiply it out. So we would have 1 over square root of 2, 0, plus 1 over square root of 2, 1. And then we would need to multiply that by itself because it will get cloned, right? So we'll have the vector product, the tensor product with itself. And then if you multiply that out, you get the 1 over square root of 2 two times. It's 1 over 2. And then you get the 0, 0 state. And then you get the same product with the 0, 1, and then with the 1, 0 and the 1, 1. And you end up with this expression. So there's just one step skipped. That's why I didn't see it right away. Okay, cool. So this allows us to state these three statements. And now we can use some linear algebra to further modify them. So first, we are going to take this state here. This guy, and write it out. And the only thing we're doing is we're moving the G operation inside of the parentheses. And since it doesn't act on a scalar, we just get the G on this vector and a G on this vector. But we know what the G will do on those two vectors because we've already written that out up here. So what this one does is it's going to turn the 0, 0 into 0, 0, and the 1, 0, it will turn into 1, 1. Okay, but now if we compare the results of A applying G before, so either first multiplying out the two qubits and then applying G, or moving G in and applying the qubits, so comparing this guy with this guy here, we see that this result that we wrote here is not the same as this result that we got before. Okay. Why are those two not the same? Well, they're not the same because apparently there cannot be a G that performs this transformation. I'd say, wait a second. Is that true? I mean, we just picked here a random superposition. Yeah, but if you cannot copy that random superposition, you won't be able to copy in general. Are there some things you might be able to copy? No, not in general. So in a standard computer, you copy things all the time. That's how a lot of things work in a standard classical computer. So those type of operations that you're used to in a classical computer, you cannot use in a quantum computer. Nice benefit of it is you cannot, as someone eavesdropping on a conversation. So if you have Alice and Bob talking to each other and Eve right here is trying to interfere, she's not able to take the qubits that Alice sends, take them, copy them, and send a copy back to Bob so that he doesn't notice that she did something with it. That's nice that copying can't be used to interfere with communications. Um, the problem really comes from the world of superpositions. As long as we take specific qubits, like the ones that we had up here, if we only use these qubits, the 0 and 1s, that's fine. Those can be copied with a gate G. So those qubits are fine. The problem is as soon as you take a qubit and put it in superposition, then you're no longer able to copy it. And so this is another sign for quantum computing being a more general type of computing compared to classical computing, because there are certain things you cannot do in the general quantum computer, but in a subset of it, you can do it. And those are all the things that we do in a classical computer. Great. So that's the no cloning theorem. And you might want to write out in your study journal why quantum computing is more general than classical computing. That's might be something you'll hear again in your future, and you want to be able to respond to that discussion. Great. Now the next thing we're going to talk about is the so-called Bell circuit. And we need to understand this circuit so that we can finally demystify the terms superdense coding and quantum teleportation. So Bell's circuit looks like that. It has a Hadamard gate in front of one of these C0 gates. And so the input to it would be two vectors, like both on state 0, 0. So you could write out the Bell circuit like that, put the two zeros here on the left. Those are our inputs. And then what does the Hadamard gate do? It will put the two into an entangled superposition. So the Hadamard gate itself is going to just put the 0 vector into superposition. And then we saw before that the C0 gate is able to take the superposition and the 0 to put it into this entangled state. Great. So simply speaking, if we apply the Bell circle, the B here, to the state 0, 0, we're going to get out the entangled superposition. You can also show in your journal that you can run the vectors 0, 1, 1, 0, 1, 1 through it, and then you're going to get these other 4 outputs. And these outputs are all going to be orthonormal vectors. So they form an orthonormal basis, mutually orthogonal and all length of 1. And so they are what we call the Bell basis. Great. One thing that's cool about all of the orthogonal matrices, all of them, is that when you calculate the product of their transposed with the original matrix, consisting of the columns of the basis, then you're going to get the identity matrix. This was sort of the test that we applied to figure out if vectors are forming an orthonormal basis, right? So what's interesting for our gates is because they're reversible, all of these reversible gates have the property that their transposed is the same as the matrix itself. So if you take any of the Pauli matrices and transpose them, you're just going to get the same one again. And if you multiply them with each other, then you're going to just get the identity. That means if you take any of these reversible gates and apply it twice, the second one will undo what the first one did. So if this is the Bell circuit here, if we take the inverse of it and now put in as inputs, for example, this superposition here, then this entangled superposition, then out comes just a 0 and a 0 qubit. And so that would be quite nice because it will allow us to send message in superpositions that can then be run through the inverse circuit in order to get the inputs back out. Right. So let's apply this in a first situation. And this is the superdense coding, one of these words that just sounds like it must be amazing because I don't really understand what it means, but it sounds super, right? So what is superdense coding? We have again our friends Alice and Bob. They both have spins in an entangled superposition. Now Alice would like to send 2 bits of information to Bob, either 0, 0, 1, 0, 1, 1, 0, or 1, 1. And she wants to do that just using a single qubit. I don't know what to qubit. Let's fix that. This looked like some weird Roman god of love. Okay. So the way Alice is going to do that is by using Pauli gates to change her electron before sending it. So she has an electron and she's going to run it through a circuit, and she will either send it through the I if she wants to send the information 0, 0, through the Z gate if she wants to send 1, 0, and so on. So depending on which 2 bits she wants to share, she selects a specific Pauli gate, which will then put her qubit into one of these superpositions. So, Alice has one and Bob has one. Alice uses hers, puts it, which is in this state, puts it through one of these gates, and then ends up in one of these 4 gates, which are just the Bell bases. So Bob receives the qubit and then uses the inverse Bell gate. And so depending on whatever Alice sends to him, he will get out 0, 0 or 1, 0, 0, 1 or 1, 1. So Alice is able to use this 1 bit that she sends to Bob. It is 1 qubit to send 2 bits of information to Bob, if the 2 qubits have been already entangled. So is that great? Is that super dense? Yeah, it's better than having to send 2 bits to communicate 2 bits. You send 1 qubit to communicate 2 bits. So effectively half of the information. It sort of requires that everyone has entangled qubits for this to work, which can be a bit annoying. However, what I understand so far is that if you want to build a quantum network, that this idea of using pre-existing entangled qubits to send 2 bits for the cost of 1 qubit is supposedly increasing the amount of throughput that you can have. And so people consider this the basis of quantum network technology. I'm still trying to wrap my mind around it. But in a sense, superdense coding in my mind means right now I can send 2 bits at the cost of 1 qubit if everyone already has entangled qubits. Good. We're here about demystifying things. Quantum teleportation, what's up with that? Now we're in a situation where Alice and Bob have again their qubits in superposition, but Alice has another qubit. And that second qubit that she has is in some state A0, B1. And she wants this particular second qubit that she has to be sent to Bob. Now, you cannot measure it, but in the moment where she would measure it, she would either get a 0 or 1 out, so she would destroy the superposition. So she doesn't really know what A and B are, but she still wants to send A and B over to Bob, who will also never know what they are. You can measure it and get 0 or 1 back. But still, is it possible to send all of the information of Alice's second qubit over to Bob? And it turns out it is. What we can use is this setup here. You can see it looks quite similar to Bell circuit. We are having first a CNOT gate and then a Hadamard gate. So it's kind of the inverse of the Bell circuit. And up here comes Alice's second qubit, and down here are the 2 entangled qubits that Alice and Bob have. So this qubit in the middle, Alice has it and Bob has it. The one on top only Alice has, the one at the bottom only Bob has. So the goal is to run through this and have at the end Bob have the same qubit that Alice has. So if this guy ends up being down here at the end, then quantum teleportation took place. All the information from Alice's qubit was transferred into Bob's qubit. So what does the C0 gate do? Well, at the beginning here on the left side, we are just having the tensor product of the three qubits. So we write it out as such. It's important to remember that we read from left to right. So this is Alice's qubit, this is Alice's qubit, and this is Alice's qubit. And these ones here, they're Bob's qubits, right? This is Bob and this is Bob. Everything else belongs to Alice. Okay, so if we have this, we can get rid of the tensor product by multiplying it out. And so you've seen such algebra before. The first zero is just written here, and we just write it a bit differently, right? We have the tensor producted with the 0, 0 state, and we just move Alice's 0 over into Alice's other one, so that these ones here are the 0, 0s that Alice has, and this here is Bob's qubit. And then the 1 over square root of 2a term just stays there. And you do that for all of the 4 terms, and then you end up with this expression. If you send this expression now through the C0 gate, which is what we do here, then the C0 gate is going to take the 1, 0 and turn it into a 1, 1, and the 1, 1 into a 1, 0. Right? This C0 gate was permuting the basis vectors. Okay. And then, of course, we also have this Hadamard gate, and we know that the Hadamard gate takes the 0 and 1 qubits and puts them into superposition. So we get, for the 0, we get a plus here, and for the 1 state, we get a minus here. Okay, so if we apply this Hadamard gate as well, then we see here this 0 state going into this superposition, and the 1 state here going in this superposition, and so on. So these green highlighted states belong to Alice's qubits, and the orange ones are Bob's qubits. And so what can Alice do now? Alice has 2 qubits, and she can measure them. If she measures them, she will either measure 0, 0, 0, 1, 1, 0, or 1, 1. And if she measures any of these states, then she knows Bob's. So let's say she measures this state here, the 0, 0. Then she knows for a fact that Bob will be in this state. So by knowing what Alice's measures, she knows the state of Bob's. And those states are all looking somewhat similar. You can see here, there is just, it all has the A's and the B's and the 0s and 1s, and sometimes plus, sometimes a minus. So what she can do now is she can call Bob and tell him, hey, I measured 0, 0. If she measured 0, 0, then Bob knows his qubit is in this state here. And that is the state that Alice wanted to send originally. So they're done. But if Alice tells Bob, hey, I measured 0, 1, 0, 1 is this guy here, then Bob is in this state. And now if Bob wants 1, 0, B1 to come out, he has to swap the 1 and the 0 around. And we saw that the X gate is doing that. And you can go for the other cases and see that no matter what Alice measured, she will be able to communicate to Bob which gate to use to either change the phase or flip the coefficients and change the phase, so that he will end up with exactly the qubit that Alice wanted to send originally. And that's quite cool. So that's the basic idea of quantum teleportation, that after using this inverse Bell circuit and telling Bob what Alice has measured, Bob will be able to apply the right gate to put his electron into the target state. And so what is quantum teleportation? Quantum teleportation means one person has 2 qubits. One of them is entangled with a qubit another person has. And this other independent qubit, the first person is able to take the information in the independent qubit and somehow merge it into that other qubit that is already entangled, and thereby putting the entangled qubit in a possession of the second person into a state that can be, through this last gate, corrected so that with the information of 2 bits that Alice shares, Bob will be able to get a qubit in one of an infinite amount of different superposition states, A naught plus B1. So is this great? Is this teleportation? Alice and Bob can be far away from each other. Initially, Alice and Bob's entangled qubits don't know anything about Alice's second qubit. After that operation, Alice's second qubit will be effectively what Bob has. Alice now has measured. She has only a 1 and a 0. She just has basis vectors. But Bob has this qubit that Alice previously had. So yeah, this is a form of teleporting all of that information over. Does Bob know now what A and B are? No, he doesn't. He can measure that thing and get a 0, 1 out with a certain probability, but he can only measure it once, then it's gone. So yeah, how useful is this thing? It might be super useful. I don't know, friends. I'm still learning about this myself as we're going. But this is what quantum teleportation is in a nutshell. Take the information of one qubit and give it to someone else that happens to already share an entangled qubit with you. Okay, great. So everything on one slide here, the 2 buzzwords, superdense coding, quantum teleportation. One of them means superdense coding. Alice wants to send 2 bits using just 1 qubit. In a quantum teleportation case, Alice wants to send 1 qubit using 2 bits. Wonderful. They use a very similar structure for superdense coding. Alice encodes using polygates, and Bob decodes using a reverse Bell circuit. In the other case, Alice encodes using a reverse Bell circuit, and Bob decodes using polygates. Okay, great. And I just looked it up a week ago or so, a couple of weeks ago now. There was an article that came out, finally realizing ultra-high capacity quantum superdense coding on quantum photonic chip in one of the NPJ Nature journals. So people are currently publishing about this, and you might run into words like that. Superdense coding on quantum photonic chip. What does it mean? Well, probably someone said to send 2 bits at the cost of 1 qubit. Or here from last year, quantum teleportation achieved over internet for the first time. So someone was able to use the internet communication channel. You can send electromagnetic waves through there, photons through there. I don't know exactly what they sent through there. It says a quantum state of light. So some photons were polarized, entangled, and a different photon state was being used to manipulate one of them, and then boom, the second entangled quantum state was changed so that it had the state of that initial photon that we wanted to copy over. So quantum teleportation worked. It's not copying, sorry, not copying, teleportation, because the guy that had its original information does have no information anymore. It was measured. It's something else now. Okay, so these things are currently happening in science, and so you might encounter these words. Just stop thinking about someone beaming someone from planet A to B when you hear quantum teleportation, or superdense coding, putting a huge neural network on a very tiny GPU or something like that. Those are not the ideas here that are important, and so I hope that you come away from this discussion with a good understanding of what's going on. Okay, cool. Then there are a couple more topics that the book goes into. I don't think that they're of very high import for us. They're interesting, and we can discuss them in class if you want to. But there's this algorithm for basic error correction. I'll let you read it in a book, and if you have questions for it, I'm happy to discuss it with you in the class. And then also for how do you correct when there was a bit flip, when something went wrong in your data storage or so on. And there's some good ideas of how to do it, but we can discuss that as time moves on. Okay, so with this, I think we have a solid foundation to go into quantum algorithms. See you there next time.